Okay, so let's start. So we'll start with hidden Markov models today. So in the last class, we discussed about Markov chains. Just a quick recap. If I mention random variables like z1, z2, what is the joint PDF? I have 4 random variables z1, z2, z3, z4. What is the joint PDF of these 4 random variables? Quick. P.
Without the diagram of connections.
Without connections, you cannot say. Okay. So this is a directed acyclic graph. Directed because every arrow has a arrow header, and acyclic because it should not make any cycle. Means no path in the graph should end at the same point. Means it should not be cyclic. Let's say if I start from Z1 and I follow the arrows and I reach back Z1. That is a cyclic graph. But this graph should be acyclic. Then I can use this DAG or directed acyclic graph to represent a PDF. So what is the PDF here? Probability of, okay, in general, it is Z1, Z2, Z3, Z4 in general. But for this case, it will be, yes, who would like to tell? Yes? What is the PDF?
Z4 given Z2, Z3, Z2 given Z1, Z3 given Z2.
And
Z1.
Yes. Good. So you start from anywhere. It's this PZ1, PZ2 given Z1, PZ3 given Z1, PZ4 given Z2, Z3. Right? That is the DAG. If I give you, if I don't give you any conditional independence conditions, then how will the graph look like? If I don't give you any conditional independence conditions, this is the kind of PDF. Now draw the graph. This is conditionally independent, right? If I know Z2, then P of Z4 given Z2 is independent of Z1 and Z3. No, sorry. P of Z4 given Z2, Z3 is independent of Z1. Right? P of Z2 given Z1 is independent of Z3. So that is okay. Now if I don't give any conditional independence conditions, if I don't give any conditions of independence, then how will the graph look like? Anybody has drawn it? If I don't give you any independence conditions, it's the most general joint PDF. How will it look like? This is not a directed graph, first of all. It has to be a DAG, directed acyclic graph. This is not a directed graph.
So you have to make a DAG.
Yes. If you want to read more about these topics, you can go to PRML book, Pattern Recognition and Machine Learning book, which is also there on the home page, the first course handout. This book explains these concepts and related concepts in details. In this class, we will just be covering like very important ones, which I need to explain HMMs. But if you want to read more, then read the book. Chapter number 9, probably 8 or 9, something. Graphical models. Done? Nobody is able to draw very soon. Okay, it's fine. No, don't worry.
DAG is some without any dependence function, we cannot say it should be DAG. It should be
You can. Okay, so you have written is P of Z1 into Z2 given Z1, Z3 given Z2 Z1. Very good. Correct answer. So how will you say? If you apply the chain rule, it becomes P of Z1 into P of Z2 given Z1 into P of Z3 given Z2 Z1 into P of Z4 given Z1 Z2 Z3. That's it. And draw the graph. Simple chain rule, right? How will you draw the graph now? I'm just writing 1, 2, 3, 4. Z1 into Z2 given Z1, Z3 given Z2 Z1, Z4 given all three of them. That's it. Right?
What if we open the chain rule in not a
Yeah.
sequential fashion?
So this DAG is not unique, right? That's what you want to say. This is not unique. There could be multiple DAGs which represent this joint PDF. Okay? Good. Okay, now just a trick question. Write the PDF for this. There are no connections here.
We need all the marginal PDFs will be in a product.
Huh?
All of the marginal PDFs will be in a product.
What does that mean?
PZ1, PZ2, PZ3.
They're all independent. PZ1, PZ2, PZ3, PZ4. Easy? Right? Take care. Good. Now, let's see what is a hidden Markov model. So, in hidden Markov model, we have seen the structure. Right? Let's say this is Z1. Is it a DAG? It is directed and it is acyclic, so it is a DAG. And P of Z1 into X1 given Z1, Z2 given Z1 into X2 given Z2, like all that HMM thing, right? This thing is familiar to you, right? And if you remember, we had written finally the joint PDF of an HMM, which is P of X1 to up to X capital N, comma Z1 to Z capital N. This is equal to P of Z1 into the product P of Zn given Zn minus 1, where n varies from? 2 to capital N. 2 to capital N times the product Xn given Zn. N varies from 1 to capital N. So, this set of PDFs, this is the initial probability or initial state probability. This is the, what is this? Transition probabilities. And these ones are, what are these ones? Emission probability. Yeah, you can also call observation probability or emission probability. All right. this is how you write an HMM. Okay. Let's discuss them one by one. First thing, I have already discussed that all the z's are discrete random variables. All the z's are discrete random variables. They must be discrete random variables. And x could be discrete or continuous, doesn't matter. Both are allowed. Means HMM can handle both of them. Okay, now let's consider the initial state probability. P of Z1. What kind of PDF can you take here? P of Z1. A Gaussian PDF? Yes or no?
No.
Why?
Because it is a continuous.
Yes. So Z1 is, if Z1 were a continuous variable, random variable, then we would have taken a Gaussian. This is not continuous. Then what will you take here? Yeah, so basically Z can take finite number of values and PZ1 has finite number of, it's a PMF, probability mass function, right? So what kind of PDF you can take? Bernoulli is for two values. Huh? Multinomial. Yeah. Multinomial. No, not multinomial. No, multinomial is different. It's
there are finite states and you can choose uniform.
yeah, it's a PMF basically. It's a PMF. Not necessarily uniform, it could be non-uniform. Yeah. It is basically a PMF. Probability mass function. Which means it is like a k-dimensional vector. Right? If there are k states, then this is a kind of k-dimensional vector. So it's k numbers and their sum is equal to 1 and they're all positive. Right? All positive numbers with sum greater than 1. Let's call them as pi k. P of Z1 equal to k is equal to pi k, where k can be 1 to capital K. And the property of pi k is that pi k is greater than equal to 0 and sum over all pi k is equal to 1. It's a PMF simply. Okay. Clear? Very easy to save your random variable. Finite number of learnable parameters, you can say. How many learnable parameters here? Quick question. K minus 1. Right? Not k minus 1. Okay. Let's consider the next thing, which is the transition probability, or we call it state transition probability. P of Zn given Zn minus 1. What PDF will you use here? What PDF? What PDF will you use here? Gaussian? Why not Gaussian? Yes. So my Zn is a discrete random variable. Zn minus 1 is also a discrete random variable. Then? Huh? It's again a PMF. Okay. Do you think it will be good if we take some examples so that you can easily think about it? Let's give some example of where such a model can be useful. Take some example that will help you to think along.
Z has to be some sort of a selector variable. So,
Yes.
So so if we have a system with finite states or finite bins that we have created.
Give some example.
For example,
Temperature. Let's say seasons. There are 4 seasons. My latent variable is a season, and my observed variable could be temperature. Okay. So my x is temperature. It could also be precipitation, right? Rainfall. So anything, humidity, precipitation. RH is relative humidity. Precipitation is the amount of rainfall which you see in every day. Let's say precipitation per day. And my Z is season. Let's say there are 4 seasons here. Summer, rainfall, rainy season, winter season, then spring season. I'm considering 4. In India they say there are 6 seasons, but I will consider 4 of them. Summer season, like May, June. Rainy season is about July, August, September. Then winter season is December, the peak winter, January. Then spring is afterwards, March, April, right? Okay. So now, what is PZ? There are 4 seasons, so just 4 numbers. What is state transition probability? Okay, how many parameters? How many parameters here? Let's make a graph. Let's make a table. So here we have the Z n minus 1. Here we have Zn. Okay. Summer, rainfall, winter and spring. Summer, rainfall, winter, spring. Right? If yesterday was summers, what is the probability that today is also summers? Large. It's a large probability. If yesterday was summers, what is the probability today's rainy season? It will be something significant. If yesterday was summers, what is the probability today is winters? It should be 0, because after summers, generally we never see winters coming abruptly. If yesterday was summer, what is the probability today is spring? 0. So from summer, I can transition either to rainy season or I can stay in summers only. Right? So let's give some numbers. Maybe 0.9 for summers and 0.1 for rainy. Okay. Now if yesterday was rainy season, what is the probability today is summers? So yesterday was rainy season, what is the probability today is summers? Close to 0. Okay. If yesterday was rainy, today can be rainy, so this will be large value. Yesterday was rainy, today is winter. Something positive. Then yesterday was rain, today is spring, 0. That is not possible. So, okay, now here, yesterday was rain, today is summers. Although theoretically you will say, let's put it 0. But I would say sometimes it happens that rainfall comes and suddenly there is again so much hot. People say Summers are back. So let's model it in that way. This is our model. Okay, I just heard something very interesting. Hear carefully, listen to this carefully. Every model is wrong. Every model is wrong. Some are just useful. Where did you hear this? Okay, it's there. All models are wrong, some are useful. So this model is also wrong, but it is a useful if we make it properly. Because model is just a model, huh? Don't trust it too much. That's why we are today these days trustworthy AI. Can we trust our models? But some people who are like not very knowledgeable, they just trust the model and they say model is everything, and then they end up in trouble. There was a survey done in America. I think I have told it before that people were in a fire exit in a room where fire exit sign was showing this direction, but the robot was saying this direction. So which direction will you take? So most of the people said I will follow the robot. So this is because robot also uses a model, but it can be wrong, or it is wrong. Maybe sometimes right also. Okay, so in our model, let's give this as 0.1, this as 0.1, this as 0.8. Okay, if yesterday was summer, what is the probability today is winter? Oh, sorry. If yesterday was winter, what is the probability today is summer? Yesterday was winter, today is summer. 0. If yesterday was winter, today is rainy season. Huh? Okay, let's take it 0. Let's keep it simple, 0. Sometimes it rains in the winter season also, but we don't say it's rainy season. Winter and spring, let's give it 0.1. And winter, let's give it 0.9. Likewise, spring, yesterday was spring, today is summer, high probability, let's say 0.1. Yesterday was spring, today is rainy, never happens. Let's say this is 0.9. Okay, so tell me this, what kind of PDF is this? It's again a PMF, but it's multiple PMFs now, K PMFs. Huh? How many trainable parameters or unknown parameters? Or how many parameters in huh? K minus 1 square.
K square minus K.
So K into K minus 1. Every PMF has K minus 1 and there are K PMFs. So K times K minus 1. Right? Alright? Some people are not participating. Following? Okay. I'm sorry. Maybe you are participating. I'm not looking at you. So this matrix is generally called as state transition matrix. Right? This matrix can be called as the state transition matrix. And you can call this as AJK. That probability of that Zn, let's say this is J, this is K. That probability of or let's call it as this is K, this is J. Okay, anyways, so probability that Zn is J given Zn minus 1 is K. ठीक है? Done. There is another way to draw the whole thing. What I will do here is now see n and n minus 1, the n is basically evolving with time, right? N plus 1, n plus 2, n plus 3. So you can take n on the x-axis and take all the states on the y-axis. Let's say this is my z1. I'll just write 1, 2, 3, 4 just to make it more legible. This is n equal to 1, 2, 3, etc. so on and so forth. So, and this is z. Sorry. So Zn equal to k. So let's say I'm sitting here, then I'm making a transition here. I'm sitting here, I'm making a transition here, and I'm making a transition here, like that. This is called a trellis. It's called trellis. That you are sitting here, then you make transition here, then you are at n equal to 1 you are here, n equal to 2 you are here, n equal to 3 you are here. In this way you keep evolving, means the state, you keep jumping, the state keeps changing, right? Just we will use it little later. Just this is the kind of representation for transitions. Now let's talk about the emission problem.
Is this specific path or could be any path?
This diagram is called the trellis diagram, which means where you represent all the states with respect to time, and then here you can represent either single path or multiple paths. So, trellis. Emission probability. What is this? Probability of xn given zn. Okay. What is this? Is it PMF or Gaussian or uniform? It can be anything. So depending on the nature of x, if x is discrete random variable, then it will be a PMF. If x is a continuous random variable, it will be a PDF. And PDF could be, so many PDFs are available to choose from. Gaussian PDF, uniform PDF, or Bernoulli PDF, and Gaussian mixture model, so on and so forth. So, which means, can you give a, for your example of summer, winter, the season example, can you tell me how will the PDF look like? Let's say
Gaussian.
temperature, huh?
Gaussian with mean variance.
Let's use Gaussian with some mean and some variance. Let's say for summers, P of xn is some particular temperature given Zn is summers. How will it look like? This is my xn or t. How will the probability look like? Probability of xn given Zn is summers. How will the PDF look like? This is 0 degrees Celsius, this is 50 degrees Celsius.
Close to 40 degrees Celsius.
So let's say the mean will be around 40 and variance will be something, right? And then let's take about, now what about the winters? In winters, how will it look like?
Well,
About 10 degrees Celsius, right? So something like this, right? I'm just to give you an idea how emission probabilities look like. Okay, good. You want to see this? This is a hidden Markov model. Now, how do we use the hidden Markov model? If I give you a hidden Markov model, you can generate data from it. It can be used for generative modeling, right? I will say, okay, I want to make a video game. In the video game, I should get all the seasons, and I should get good temperature as per, and then you just make the video game for 1 year, means that, or movie, let's say, one animation movie for 1 year, and you design that how the temperature will look like for over the entire year. So you can you can train your hidden Markov model on your previous data. Let's say you want to make the movie shot in Kanpur. You have all the temperature data for past many years in Kanpur. You train your HMM there. How you train, we will discuss later. Let's say you trained it and now you are using the HMM to make your movie, right? Where you are showing the temperature at on every date, let's say. Right? And it's not static. There is not a rule that, okay, on, what is the date today? 29th, 30th of September, it should be 30 degrees Celsius. It's not like that. It's a probabilistic model. So sometime it will be 30, sometimes it will be 40, sometimes it will be 20. So it's a probabilistic model. You get lots of samples, lot of variation. So our movie does not look like a dull movie. It has some variations. Okay. So the first thing which you can do with your model is sampling. Sampling means generating new data. That follows the PDF. The joint PDF which we have seen. So generating new data that follows the given PDF, which means the HMM. HMM is a model for the PDF, right? HMM represents a PDF. How will you sample from an HMM now? If I give you an HMM, how will you sample? How do you sample an HMM? Sample means taking.
Sample from the initial state probability, then you keep sampling from, then you sample from the emission probability HM.
Okay, let's say you are saying first you sample your Z1 from P of Z1, then
X1 from P of X1 given Z1.
let me call it as Z1 dash. It's just one value of Z1 which you have sampled. Then what will you do?
X1 dash from P of X1 equals X1 dash given Z1 equals Z1 dash.
Okay, so you fix your Z1 now to Z1 dash, and from that you get this marginal PDF. Like you saw here, summers in wind. So you fixed your season. Then given this PDF, you will sample from the temperature, right? So okay, you got X1. Then what will you do next?
Z2 dash is sampled from P of Z2 given Z1 equals Z1 dash.
So now you will sample, okay, yesterday was summers, what is the season today? And you got a season, call it as Z2 dash. Then sample X2 dash. Right? You got a new temperature for the new season. And in this way you keep going. So let's say your chain was like this, Z1, Z2, Z3, and here X1. So first you sample Z1, then sample X1, then Z2, then X2, then Z3, then X3. In this way you keep sampling and keep going forward. Right? That you get one chain, then you can sample another chain, multiple chains you can sample, right? Okay, now this is clear. Okay, in general, I'm just now telling this is only for HMM, but in general means for any DAG. In any DAG, any DAG can be sampled by starting from
Going in the topological sort order.
where do you start?
Any node with degree 0.
With in degree 0 or independent node, right? Starting from any right, start from any node with in degree equal to 0 in your words, and then move in the direction of arrows and keep sampling. Then move in the direction of arrows.
Basically, you need to go in the order of the topological sort for that reason.
Yes. Yes. Okay.
So what if we start from a node with out degree 0 and then we branch off to all possible states to achieve that node and then sample any state from it?
But then you will be in a kind of loop, not loop, but in a long chain. Let's say this tree starts from here, graph starts from here, ends up here. I pick this. To know this, I have to know this. To know this, I have to know this. To know this, I'll be kind of.
Total probability.
Huh?
Like a total probability.
You have to go back, but then it's like you go back to your original node, which does not depend on anything else. You sample this and then sample next, sample next, sample. So why to do this reverse process when you have to reach there only? Okay, good. So sampling is done. Sampling is easy. Given a model, you can sample it very easily. Next problem is inference. By the way, I'm following this from a tutorial on HMMs by Rabiner. It's a very old, maybe 1980s or something. This tutorial was published, and it's a very useful, very good, very well written document. Okay, where are we? Inference. What is the meaning of inference? Inference means if I give you X, can you tell me Z? First of all, understand that we generally don't observe season. Right? You cannot measure season. If I ask you what is the season today, you don't know. You have to just guess it from your model. So season is a kind of latent variable. You don't know it. You don't observe the season directly. You observe temperature, humidity, precipitation, etc. And then people have some understanding of okay, this is the season. This should be the season. अगर बारिश बहुत हो रही है तो बरसात का मौसम होगा, या फिर अगर लगातार बारिश हो रही है कई दिन तक, ओके इट मस्ट बी मानसून और रेनी सीजन, राइट? बट यू डोंट सी सीजन डायरेक्टली. सो इन्फ्रेंस मीन्स to deduce z. That's it. To deduce z. What do we know? We may know x. We may know previous z. So first problem is given xn and zn minus 1. Sorry. Find zn. If I tell you today the temperature is this much and yesterday the season was rainy season, tell me what is the season today. How will you tell? And HMM is given to you. I've given you the model. So model is given to you. I'm asking that this is my xn, this is my zn minus 1. Tell me from the model what is the zn today. What will your model say, or how will you deduce zn given this information and your model? When I say model is given, it means the initial probabilities are given, the transition probabilities are given, and the emission probabilities are given. Okay?
So the probability of Zn should be probability of xn into probability of Zn given xn.
Okay, let me write down. Probability of, first of all, what you have to find. What do you want to find?
Probability of Zn.
Probability of Zn.
Or that state of Zn.
Okay, first of all, let me add correction here. You want to find Zn star or Zn dash, whatever you call it. You want to find Zn star, the season today. Okay, how will you find it?
First we can find the probability.
You find the probability and then maximize the probability. Okay, so whatever is the probability.
Pzn is P of xn.
So I'm saying Zn star equal to argmax over Zn. Yes, P of
Xn into P of Zn given xn.
xn into P of
Zn given x. Plus P of Zn minus 1. Into P of Zn given x. That is Zn given Zn.
this one. How did you arrive at this?
I just thought to connect the dependencies, and then I need to apply some base theorem on P of Zn given xn to second term is
I don't know. How did you construct this? Okay, it seems to me it is not correct, but maybe you
I'm
can.
confident with the second term at least.
Okay. Okay. Fine. I have put a question mark here. Any other solution for Zn star? How will you find Zn star? Huh? Bayes rule? Bayes rule is to find probabilities, but you have to find Zn star here.
You just select the Zn with the highest probability.
What is that probability?
You calculate the probability with Bayes rule.
Oh, just tell me the first. I'll apply Bayes rule later, but first tell me the quantity you want to estimate. You're saying Zn star is equal to argmax of what?
Probability Zn given xn
Zn given
x
n.
Zn minus 1.
This is the one you want to find. Okay. Anybody has any other answer? How many of you have heard about maximum likelihood estimate, maximum a posteriori estimate, MAP and ML estimates? How many of you have heard about them? MAP and ML, MLE or MLE. You have heard about MAP and MLE? Now think about it. I've given you the hint.
Some broken maps.
What are MAP and MLE?
MLE is the value of Z, like Zn, that maximizes this probability without assuming anything about Zn. And map is when we put some conditions on Zn.
Okay. Log of P Zn upon Xn. What is this? This is MLE. And what is map? What is posterior?
So based on our DAG for the standard DAG for the HMM, Zn does not depend on Xn.
Okay.
So just
That is fine. In HMM, you factorize your graph in such a way that Zn does not depend on Xn, rather P of Xn given Zn is given to you. But if you apply Bayes rule, you can
Then I
find
need
the
to
expression.
convert, yes.
Yeah, you can find the expression for P of Zn given Xn is equal to P of Xn given Zn into P of Zn upon P of Xn, right? That is the Bayes rule. So you cannot say the quantity does not exist. Quantity exists, but the HMM factorizes it in a different way. And we can apply Bayes rule to factorize it in this way, or basically to compute this quantity, right? Okay, fine. I will now reveal the suspense. I think I will erase this. Let me erase everything. Let's start afresh. Okay, so let's first discuss the basics. What is map and MLE? If I apply maximum likelihood estimate, what is likelihood? Probability of X.
the PDF.
PDF is a complete joint PDF. P of Z and X and everything is there. What is likelihood?
Probability of occurring of the season given that we have some
Okay, that is
likely to be the
that is not likelihood.
Probability of probability of that theta given x.
Probability of theta given X, that is not likelihood.
Probability of random variable given observed data.
That is not likelihood. Okay, what is likelihood? Probability of observed data given everything else. Probability of observed data given everything else, that is called likelihood. Memorize this, like don't make this mistake. These are very basic things, but nobody taught me these things. And later when I kind of bumped into these things, I realized, oh, these things should have been taught in the class. Or maybe these were taught and I didn't take it very seriously. These things must be taught. But so P of Xn given Zn, comma Zn minus 1, whatever. So if I maximize this over, or basically argmax over Zn, that is called the MLE. So the maximum likelihood estimate of Zn is, or Zn star, this is given by argmax over Zn, P of Xn given Zn, comma Zn minus 1, comma whatever. This is called the maximum likelihood estimate. How can you estimate now this thing? Now, okay, this is the kind of by definition, right? Now you think, how will you express this quantity in terms of the given probabilities in the HMM, like transition probability, emission probability, initial probability, etc. Now you start thinking in those terms. Now tell me, how will you write it? This is equal to P of Xn given Zn, because it is independent of Zn minus 1 in HMM. And this is known to you, right? So basically you take season. You take, let's say temperature is given to you, today is 40 degrees Celsius, tell me which season it is. Okay, let's measure what was the temperature, if it were summers, okay, let me plot it like this. 0 degrees Celsius, 50 degrees Celsius, winters, winter, spring, rainy, summer. Just some approximation. Now if I tell you today the temperature is this much, what season it is? MLE. Tell me from MLE which season it is today. Huh? Yes? Be confident. Dadte kyun? हाँ, rainy season. It's rainy season. Don't be afraid to make a mistake. No problem. Mistakes are allowed in the class. So it's rainy season. So my Zn star is equal to rainy season. Okay? Any doubts? This kind of estimate is a very bad estimate. Why? It does not take into account what was yesterday. It's a very greedy. Therefore, we generally don't use ML estimate. Okay. What about map? What is MAP? By definition, Zn star is equal to argmax of what?
Posterior of Zn.
What is posterior? It's a nice term to use, but what is the meaning?
The distribution of Zn given the observation.
So when we say posterior or a posteriori probability, posterior, it means probability of what I want to estimate given everything else. So what I want to estimate here? Zn. So probability of Zn given everything else. I'm interested in Zn, so let me maximize the probability of Zn only, given xn, Zn minus 1, whatever is given to me. Okay, so this is by definition. Now we have to use HMM to estimate this quantity. Now can you express this, or can you use HMM to estimate this quantity, or to express this quantity in terms of known HMM quantities? Yes. What is that? This is equal to PZN. Making some mistake. Okay. Can we write it like this? Why? Huh?
Doesn't feel right. You have to use base rule because Xn is.
No, first tell me why this is not right.
Observed Xn is not independent of Zn.
Yeah, Zn is not independent of Xn given Zn minus 1. Okay, I think I should have told you a little bit more about graphical models. Let's do that, no problem. You can read about it in the book, PRML book, but I will just briefly tell you from what we discussed. I was about to tell you, but then I thought, okay, maybe it is too much detail. So, in the DAG, how conditional independence works. Let's consider Z4. P of Z4 given, if I am given Z2 and Z3, can I say my P of Z4 is independent of Z1? Yes. So P of Z4 given Z2, Z3, Z1 can be written as P of Z4 given Z2, Z3, because it is independent of Z1. Right? So, which means this is a child node, this is the parent. If this is the child, this is the parent. This is the child, this is the parent. Right? For this child, this is the parent. For this child, this is the parent. Oh, sorry. For this child, these are two parents. For this child, this is the parent. For this child, this is the parent. This child has no parent. Is a root node or whatever you call it. Childless node or parentless node. Okay. So, given the parents, the child is independent of its grandparents or super grandparents or whatever. Right? Given the parents, the child is independent of grandparents and super parents, but not of children. Right? So Z2, if Z1 is given, it is also independent of siblings. It's also independent of the siblings. But it is not independent of the children. Right? So that's the principle. If you want to read more about it, I think we already crossed the time. You can read it in the book, PRML book. So if you apply that here, now Xn is the child of Zn. So Zn is not independent of Xn. So you cannot write this as this. Is this point clear? Zn is not independent of xn. Zn is independent of, if parent is given, then it's super parent, like Zn minus 2, Zn minus 3, Zn minus 4. That can be removed, but not xn. Okay, what will you do in this case? Bayes rule. Let me apply Bayes rule. P of xn. Yeah, tell me the Bayes rule. Zn comma Zn minus 1 into Zn given Zn minus 1 divided by xn given right. So this is what I have to do argmax over this. Now you see, this term depends on Zn, this term on Zn, this term does not depend on Zn. So we don't need to optimize this term. So this is equal to argmax of numerator only. How will you express now these quantities in terms of what you know from HMM? Now simplify. This is equal to what is Pxn given Zn, Zn minus 1? P of xn given Zn. And what is P of Zn minus 1? Zn given Zn minus 1 only. Okay. But denominator thing, it's independent of Zn, but what it is actually, it is P of xn given Zn let me correct this is the dash the denominator term does not play any role in the optimization, but this is what the term is, right? The numerator term plays a role in optimization. And this is a known quantity from HMM, this is a known quantity from HMM. You know both the quantities. So in this way you can do inference. Unfortunately we have run out of time. Okay. Clear? So if I tell you yesterday was summers and today the temperature is 35 degrees Celsius. Now tell me what season it is today. What will you do? You will take P of xn given Zn, which means this graph, right? This is xn given Zn. And you multiply it with P of Zn given Zn minus 1. Yesterday was summers. Let's take this one. Let's say this is my temperature. I will simply not accept this rainy. I will say probability of rainy given yesterday was summers. You multiply it, like this quantity is, let's say 0.5 or something. You multiply it with that quantity, probability of rainy given summers, which was 0.1 or something, huh? So multiply that with 0.1. And then take summers, this value, multiply it with probability of yesterday was summers, today is summers again. That is 0.9 or something. This is multiplied by 0.9. So now tell me which one will be the winner? Summer will be the winner. Here it was the loser. But if you apply MAP, then summer may become the winner. Right? So, and the good thing about MAP is that it is considering not just the today's temperature, but also yesterday's season also. So that's why we generally use MAP for inference. Clear? Okay. Thank you very much. Should we stop here then? Any questions? Any questions anybody has? Okay. Thank you. Your marks are uploaded on, what is it called?